Hello there, Mr. Sutton here with the IM3 Honors 3-1 lesson on Introduction to Imaginary Numbers. In this one, we're going to be simplifying radicals with negative numbers inside, and we will be simplifying powers of I, whatever that is.
For your warm-up here, I've got two warm-ups for you. First warm-up, simplify the radical square root of 32. Pause the video and let's see if you still got those skills. Alright, so one way of doing this would be to split it up into the biggest perfect square possible times another number. So 16 times 2, each with their own radical. And then the square root of 16 is 4, so 4 radical 2 would be the simplified version of this. We're going to be simplifying radicals a whole bunch later on, so it's good to remember those skills with real numbers. But that brings us now to warm-up number 2. Solve for x in the following equation. Pause the video and give it a shot. Alright, so if you're trying to solve something with an x squared, the way we typically do that is by square rooting both sides of the equation. And we should hopefully remember that there's a plus minus when we do that. So we'll have plus or minus the square root of negative 1. But what is the square root of negative 1? Well, it can't be positive 1, since positive 1 squared gives us positive 1. And it can't be negative 1, since if you square a negative 1, you're multiplying a negative times a negative, also giving you a positive. So what is this? It's actually a number that doesn't exist. And we're going to make a special symbol to represent this number that doesn't exist, this square root of negative 1. Since it's outside the real number set, we're going to call it I for imaginary. So then we're going to define I as the square root of negative 1. And based off of this, we're actually going to make a whole new number set called the imaginary number set. And you'll have numbers in there such as I, 2I, 3I, basically any number you want with an I next to it. So at this point, some of you might think I'm crazy or just wasting your time. I mean, why spend time on imaginary numbers? They don't exist, right? Well, these imaginary numbers actually do have real uses. For example, electrical engineering, they can be used to model electrical circuits. They can be used for probability distributions in quantum mechanics. And you can also use them to do some rotations on a graph. And I mean, if you think about it, calling these numbers imaginary, but how about the number 2? Do you just see the number 2 floating around in real life? Can you reach out and touch the number 2? No, not really. It's just an abstract mental concept that helps us deal with reality, just like imaginary numbers. So now that we know about the existence of I, or the non-existence, how can we use that to help us simplify things? Well, take this expression with negative 72 inside. Now, normally, we wouldn't be able to simplify this because we would just throw up our arms and say, oh, not a real number. But now that we know about I, we can split this up into the square root of negative 1 times the square root of 72. What's the square root of negative 1 again? Oh, yeah, I. So we can make this work if we just turn that into an I and stick it out in front. And by the way, you don't have to show this step of taking out negative 1 every time. You can just take an I out and make the inside positive. I call it taking out an I. Ooh, that's kind of grisly. But let's talk about the rest of this problem now. 72, how can we split that up? Well, the biggest perfect square that goes into that after some trial and error is 36 times 2. Square root of 36 is 6, so we can call this 6I radical 2. Here's another example with a negative radicand. Pause the video and see if you can simplify this one on your own. All right, let's see how you did. So first off, got to take out that I. So this negative disappears and we've got a negative 8I outside. Next, we have to deal with 60. What's the biggest perfect square that goes into 60? Well, 4 goes into 60 15 times. Square root of 4 is 2, and 2 times negative 8I, how do we do that? Well, the nice thing about I is that, at least in this situation, it behaves just like a normal variable. So you just have to multiply 2 times the negative 8, and then whatever that is, that's going to be next to I. So negative 16 in this case, negative 16I radical 15. So here's an interesting question. If I is the square root of negative 1, what's I squared? Well, I squared would just be the square root of negative 1 squared. Square and square root cancel, so that means that I squared must be negative 1. I is an imaginary number. I squared is actually a real number, -1. So this neat little property of starting with imaginaries and ending up with real numbers does make I useful for solving some equations. Hundreds of years ago, they used it to solve the general cubic equation. We're not going to go that far, but it's just worth noting this neat property here. One other nice thing about knowing that I squared equals -1 is we can now find all the other powers of I that we would ever want to. Using the fact that I squared equals -1, see if you can find the other powers of I up to I to the 8th. All right, let's see how you did. So I to the first, we'll just call that I. We know it's the square root of -1. We're just going to express things in terms of I now, though. I squared, we already saw that was -1. How about I to the third? Well, I to the third, you could split that up into I squared times I, right? Because if you were to multiply these back out, you would add the exponents and have I to the third. Well, this is -1 times I, which is -I. How about I to the fourth? That's really just I squared times I squared. Those are both -1s, so I to the fourth then equals, that's interesting, +1. How about I to the fifth? Well, I to the fifth, that's really I to the fourth times I. What's I to the fourth? Oh yeah, 1. So this is just 1 times I, or I. I to the sixth, that's I to the fourth times I to the second. Really, whenever you see one of these I to the fourths, you really just have a 1 being multiplied by whatever else there is. So this is just I squared, or -I, or -1 rather. And then I to the seventh, that's I to the fourth times I cubed, which is just going to be -I. I to the eighth, well, that's I to the fourth times itself. 1 times 1 is 1. That's kind of interesting. So what pattern do you notice here? And how often does it repeat? That's right. It always goes I, -1, -I1. I, -1, -I1. So that's going to repeat in cycles of 4. So theoretically, if you want to find a super high power of I, as long as you know where you are in this cycle, you could find pretty much anything you wanted. The question then becomes, as we look at these two examples with I to the 98th and I to the 83rd, how do we figure out where we are in the cycle? It'd be nice if there were a quick way of doing this rather than splitting this up into a whole bunch of I to the fourths times some other number. So there's a few tricks for doing this. One is to divide the exponent by 4 and then figure out the remainder. So 98 divided by 4, that's going to be, I think, 24. It doesn't really matter. The remainder is going to be 2. And then that remainder tells you what you really have. I to the second in this case. 2, 2. It matches up. And we know I to the second is just -1. Another way of doing it is to figure out the biggest multiple of 4 that's less than this number and subtract it from this number, and then whatever's left over, well, that is kind of the remainder all over again, right? That's going to be where you are in the cycle. You could also just subtract 4s until you get down to something between 0 and 3. In any case, try one of those methods, pause the video, and see if you can figure out I to the 83rd. All right, so I'm going to use my remainder method. I know that 4 goes into 80, so that means we're going to have a remainder of 3 left over. This then is really I to the third power, which I know is -I. So this lesson is over. Imagine that. Until next time, this is Mr. Sutton signing off.